Hello everyone! This is my final project for the course Machine Learning for Product Managers offered by Duke University through the Coursera platform. The goal of the project topic, is to build a model to predict the electricity production of a combined cycle power plant which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to produce energy. The dataset consists of 9,568 early average environmental readings collected from the plant's sensors. The approach used to develop this project is the following: understand the business and the application, analyze the data, build the models, and finally, the evaluation and the interpretation of the models. The first step was to understand and get a general overview of how a combined cycle power plant works. For explanation purposes, a short video is provided with a brief description of how this type of power plant operates. Here the video.
Combined cycle technology enables power plants to generate 50% more electricity from its fuel than it would with a conventional single-cycle power system. Under this dual-phase system, two combustion turbine generators operate in conjunction with two heat recovery steam generators and a steam turbine generator. In the first cycle, fuel is burned and the resulting combustion gases power two turbine generators to produce electricity. Hot exhaust normally lost during this process is captured and routed through the two heat recovery steam generators. These units boil water to create steam, which spins an additional turbine generator and produces more electricity. Finally, the steam is discharged into a condenser, which returns the steam to its liquid state for recycling.
The available data include temperature, ambient pressure, relative humidity, exhaust vacuum, and net energy production. Each variable falls within the range shown on the slide, and here we also show which variables are independent and which one is the dependent variable. In this first phase, it is important to understand the relationships between the variables. For example, we observe an inverse relationship between temperature and energy production. This behavior is fully consistent with how the power plant works. In a combined cycle plant, higher air temperature reduces air density at the gas turbine inlet, leading to lower power output. This plot shows that temperature is very important and must be included in the model. For the other variables, we observe a negative relationship between exhaust vacuum, V, and energy production, although it is less strong and more scattered. There is also some slight non-linearity. We can partially conclude that worse exhaust vacuum reduces the efficiency of the thermodynamic cycle. This variable is also important and should be included in the model. Instead, we observe a positive relationship between ambient pressure and energy production, and between relative humidity and energy production. For AP and PE, the scatter plot is more dispersed, so this variable can be considered secondary compared to temperature and exhaust vacuum. The physical interpretation is that higher pressure increases the mass of air entering the turbine, slightly improving production. The last relationship between RH and PE is weak and highly scattered, making it harder to interpret. This could make relative humidity an optional variable. These observations are confirmed by the correlation values shown here. The data were split as follows: 80% for training, 10% for validation, and 10% for testing. The data were selected randomly to avoid bias, of course. A column with a unique ID was added to the dataset here, and a random value was assigned to each observation. As a result, 80% of data training set corresponds to this raw range. 10% of the data, validation set, correspond to this row range here, and the last 10% of the data, the test set, corresponds to this row range here. 3 linear regression models were developed with increasing complexity. Model 1 includes variable t and v, Model 2 includes tv and ap, and Model 3 includes tv, ap, and rh. The metrics used to evaluate the models are mean absolute error here, mean square error, and the last one, the R square here. We start with Model 1. I ran the linear regression using Excel, and this is the result. R square is quite high, around 92% here, meaning the model fits the data well, and the standard error is about 4-5 megawatts. Next, I tested the Model 2. We see that R square remains almost the same, and the standard error is also very similar. Finally, I developed Model 3, the most complete one. The multiple R is very high, 0.964 here, meaning the model fits the data very well. R square shows that the model explains about 93% of the variance, which is very good for an industrial application. Adjusted R square is almost equal to R square, which is a good sign against overfitting. The standard error is around 4-5 megawatts. Considering an average production of about 450 megawatts, this corresponds to an error about 1%, which is physically reasonable and realistic. The F-test confirms that the model is statistically significant. Now let's briefly comment on the coefficients. Temperature. Increasing temperature by 1 degree reduces production by about 2 megawatts. This is fully consistent with the plant's behavior and the scatter plot. Exhaust vacuum has a negative impact, consistent with previous observations. Pressure has a positive impact. Higher pressure slightly improves production, which matches the physics and a moderate correlation. And relative humidity here, at first glance, this result may seem inconsistent with the scatter plots. However, the model considers humidity together with the other variables, leading to multicollinearity. From a physical point of view, the result is still plausible. At this point, I applied the different models to the validation dataset and calculated the same evaluation metrics. Using the validation set, I computed the predicted energy production, here for example for the Model 1, the error, and the square error. And then I calculated mean absolute error, mean square error, and R squared, here for Model 1, Model 2, and Model 3. The results are consistent with the previous findings. Model 3 performs best. So, why does this happen? As shown before, R square increases while mean absolute error and mean square error decrease. There is no evidence of overfitting, and we observe gradual improvements as the model becomes more refined as expected. After selecting Model 3, I applied it to the test dataset and evaluated the matrix again. The results are consistent and slightly improved. Model 3 shows an average prediction error below 1% of nominal power. No major errors are observed, and the model is stable. Finally, the model explains more than 92% of the variability in energy production, which is very high for real-world data. At this point, I asked myself, can we do better? To answer this question, I explored linear model ensembles. The idea is to combine different models to further reduce variance and improve generalization. The explored approaches were mean ensemble and weighted ensemble. In the mean ensemble, I combined the three linear models using before, and I used the test dataset and the formula shown here. For simplicity, here I only show the results. If anyone is interested in the detailed Excel calculations, feel free to contact me, of course. As we can see, the results are good, but not better than Model 3. Model 3 performs best. Again, for simplicity, I only show the final results here, even though the performance is good, so Model 3 is the best, is also the best. The weighted ensemble was built using the same three models, assigning the weights shown on the slide, with Model 3 of course having a slightly higher weight. Again, using the test dataset. In this case, the weighted ensemble performs better than the mean ensemble, but Model 3 is still the best overall. For this reason, we can say that Model 3 is chosen as the final model. So, thank you for your attention. If you have any questions or would like to see the Excel file I use for this project, please feel free to contact me, of course. See you soon and enjoy the rest of the course.